Here I have the formulas for compound interest and simple interest. So again, real quick, just a little refresher before we get into this. Compound interest, you give me a dollar amount and an interest rate and a compounding interval, and I'll be able to use this formula to tell you how much money you'll have at the end of 1 year. Similarly, over here, you have a simple interest rate. So you give me a dollar amount and an annual interest rate, and I'll be able to tell you how much money you have at the end of 1 year. So just to warm up and get familiar with these formulas, let's do an example. Let's say I give you $100. You're very welcome. $100. And your money is going to compound at 5%, and it's going to do so monthly. So my question is, how much money would you have at the end of 1 year? Well, we just come over here to our compound interest formula and plug things in. So we have $100. And our interest rate is 5%, 0.05. And then we are compounding monthly. So we get our compound interest rate formula, our compound interest formula is this here. And we can figure out what this dollar amount is. Now let's get my calculator. So we have 0.05 divided by 12 plus 1 to the 12th power. And all of that is multiplied by 100. So we find that we have $105.12. We have $105.12. Okay, so that's good. We just got some familiarity with our compound interest formula. But let's say, okay, we weren't interested in compounding, but rather we would want to know, if we weren't going to compound, how would we get the same dollar amount at the end of 1 year if we were to just have an annual interest rate? So what I'm saying is we want the same $105.12, but we're not going to compound. So what would the interest rate be? So we start with the same $100, and what would the interest rate be? Well, we could divide both sides by 100. These would cancel. We'd move our decimal place back 2. So we would get 1.0512 is equal to 1 plus r. And then we could solve for r. And we'd find r to be 0.0512, or as a percentage, 5.12%. So this would be, okay, we're not compounding, but rather we have that $100 and we would apply 5.12% to it, and we would have the same dollar amount at the end of 1 year. And this game that we just played actually has a term for it. This game of finding, okay, we're not compounding, but we want to know how to get the same dollar amount by just using an annual interest rate. This game actually has a term, and that term, let me grab some more space. This term is actually called APR. APR, and this stands for annual percentage rate. Annual percentage rate. And if we want to come up with the formula, again, we're just basically going to be writing out what we did over here in this scenario. So we can write out our compound interest formula. A is equal to P times 1 plus, and now I'm going to write R with a little subscript for compound interest. Our compounding interest rate. So we have R sub C over K to the kth power. And then I will also write our simple interest formula. So if A is equal to P times 1 plus R sub S, again for simple interest rate. So we have these two things, and now we want to equate them. So both A and P in both formulas are the same. So we can do this. We can divide both sides by P here. Those will cancel. We can divide by P down here as well. These will cancel. And now we can equate these two things. So we have 1 plus R sub S is equal to 1 plus R sub C over K to the kth power. And again, we want to solve for R sub S because that is APR. That is saying, okay, here's our right-hand side talking about our compounding conditions, and we want to find what the annual interest rate would be to give us the equivalent dollar amount at the end of 1 year. So we're really solving for R sub S here. R sub S, so we'll subtract 1. So we have R sub S is equal to 1 plus r sub c over k to the kth power minus 1. And this right here is our APR formula. This right here is our APR, and r sub s is APR, the annual percentage rate. Now, we want to use this formula that we just had and get some practice with it. So let's go over here and do an example. So let's just say I want to know what the APR, what is the APR? What is the APR of 10%? 10% compounded monthly. So why don't you pause the video and give that a try on your own. All right, assuming that you've given it a go, again, all we're doing is just using this formula that we just came up with. So we have that APR is equal to, we have 1 plus, and r sub c, we're finding 10% compounded monthly, so this is going to be 0.1 over, and k is going to be monthly, so that's 12 over 12 to the 12th power minus 1, and we can figure out what this is on our calculator. So let's go figure out what that is. So we have 0.1 divided by 12 plus 1 to the 12th power and all of that is going to be subtracted by 1. So we find our APR is 0.1047. 0.1047 is equal to 0.1047. And as a percentage, that is 10.47%. And again, what is this saying? That's saying, okay, here's our compounding conditions. This is the equivalent annual interest rate to give us the same amount of money at the end of 1 year if we were to compound our money at 10% monthly. That's all it's saying. And you might be wondering, okay, great, you're talking about APR, but what are we doing talking about APR in a calculus class? Well, hopefully in the next example, you can see why. So let's do another example. Rather than finding the APR of 10% compounded monthly, I want us to find the APR now, the APR of 10% compounded continuously. And what does that mean? Well, that's saying, okay, we want to compound as much as possible. So we're not going to have a k value here like 12 or 365, but rather we're going to take the limit as k goes to infinity. So our APR formula under compounding continuously is going to look like this. It's now going to be the limit as k goes to infinity of 1 plus, in this case, 10%. So we have 0.1 over k to the kth power, and we're still subtracting 1 from that. So again, this first part here, this limit represents compounding continuously, and we want to find the APR now. So how do we do this? Well, this is the connection we want to make. If you can remember, we've been dealing with a certain kind of limit lately, and that is the limit as n goes to infinity of 1 plus 1 over n to the nth power, and we found that this is equal to e. So we want to use this fact in order to solve this APR problem. And in order to do that, we have to get this limit to look like this limit over here. So how do we do that? Well, we can make a substitution. Let's make a substitution. Let's say that 1.1 over k is equal to 1 over n is equal to 1 over n. And we can make this substitution here and checking our limits. As k goes to infinity, this will go to 0. And as n goes to infinity, this will also go to 0. So we can make that substitution and still say that the limit as n goes to infinity is good. So we now have, under this substitution here, the limit as now n goes to infinity of 1 plus 1 over n, making that substitution. And then k, if we wanted to solve for k, we can multiply both sides by n and both sides by k. So we would have that 0.1 times n is equal to k. And then we can fill this in up here as well. So we have 0.1n as our power, and we're still subtracting 1. So now we're super close. Again, we want to get this into the form where we can leverage this fact that we know this limit is equal to e. So I'm going to rewrite it one more time using a limit rule. So I'm going to say that the limit as n goes to infinity of 1 plus 1 over n to the nth power, and all of this is going to be raised to the 0.1 power. This is just a limit rule that we can use, a limit property, and this is still subtracting 1. And what is this inner part of these parentheses? Well, it's the limit that we know. It's e. So this actually becomes, I'm going to grab some more space. This is actually e to the 0.1 power. 0.1 power minus 1, and that is our APR. APR, and if we wanted to figure out what this is, pull up my calculator, and we can plug that in. So we have e to the 0.1 power minus 1. And we find our APR is 0.105, and if we were to round, 2. So 0.1052. This is equal to 0.1052, or 10.52%. And again, why, if we were to compare this with our earlier example where we were just compounding monthly, it makes sense that this percentage is higher because we're compounding more often. We're going to have more money at the end of 1 year on our dollar amount because we're compounding more often. So it makes sense that our APR would be higher. And again, not only did I want to introduce you to APR, but really I wanted to show you that we could use this fact that E is this limit in order to solve this cool APR problem.